So we are continuing our investigation of the periodic table. And we're starting off by providing some additional vocabulary for you guys. Primarily, the regions of the periodic table have different names. So a couple of things that aren't on here, let me change the contrast a little bit so we can see it. One thing that I'm going to talk about are rows. And when I say row, I mean left to right. So if I say a row, I'm talking about directions that way and that way. And that is also called a period. All right, well, we also have directions we can go up and down, and I will call that either a column. So I'll say a column, and I'm talking about up and down, and that's also known as a family. And part of the idea is when you talk about human beings' families, one of the things is we all have similarities usually in our family. We have common genetics. Well, when we have chemical families, we also see similar characteristics. So it's a good name for them. So in this first column, the family is called the alkali metals. And that's already listed for you. And you're going to see that several of these columns have specific names. So if I were to say alkali metals, I'm talking about lithium through francium, that family. Now remember, hydrogen is here. We're just not showing it because it is not considered a metal, but it does belong, for some reasons we'll talk about later, in that column. But the alkali metals start with lithium and go down. Next to those are the alkaline earth. This block right here, that we refer to as the D block elements for their electron configurations, are known as the transition elements, but transition metals is more often used. So we would call these the transition metals, but more generically called the transition elements. Then we'll go over to this column, the last family here is known as the noble gases. They used to be called the inert gases, but they were found that they were not completely inert, all of them, so that was not a good name. Okay, then the second to last column is called the halogens. Now, there are names for other families that you can read. They're a little more obscure, and they're just not going to be required for this class. But a few more. The representative elements, what they're saying is those are the elements in the S block from here to here, and the P block from here to here. Those are the representative elements, not including the transition elements. That's what that's trying to say. All right, so everything else is pretty labeled. So you see these would be the lanthanides, these would be the actinides. So this will be a pretty handy table if you're not familiar with those family names yet. All right, so just a little bit of a test to see kind of what the questions might be like that I would ask. Could you answer these? Select the symbol of the element that fits the following descriptions. The alkali metal in the fourth period. So you need to know what alkali metal and fourth period mean. So this periodic table is labeled for you, so it would probably be better to use the one you'd have on the exam. So the alkali metal in the fourth period, here's the alkali metal. The fourth period is if we go 1, 2, 3, 4, and label the rows, it would be potassium. Okay, so that would be the alkali metal in the fourth row or the fourth period. K, potassium. The halogen in the third period. Well, when you're familiar with the periodic table, you recognize that the second to last column is the halogens. And the third period would mean the third row. So we'd go there and that'd be chlorine. Okay, so basically, the first part of this chapter is vocabulary and feeling comfortable with the way the periodic table is mapped out. Okay, so the rare earth element with the lowest atomic mass. All right, so one thing I want to show you is that there's no way to look at the periodic table and know exactly what the rare earth elements are. Now we're going to show you that they're right here, but what I meant to do before class, before I found out my email was messed up, and it took me some time to try to deal with that, I wanted to show you where you can find this information in the textbook. There's a part of the chapter, and it just outlines what the rare earth elements are, and I just wanted to show you so you're not necessarily taking my word for it. So right down here, it talks about the rare earth elements, and I just want to show you. It says right here, starting with where my finger is, the elements cerium through lutetium, I guess, lutetium. I just want to make sure I said it right. The cerium through lutetium have similar properties, and they occur together in nature along with scandium, eritrium, and lanthanum. The natural abundance of these elements in the Earth's crust is less than 0.05%, and they are collectively referred to as the rare earth elements. Now, I want to show you that just because I am using the book as reference for that, and I'm going to explain why I'm clarifying that. So basically, it's saying that scandium, eritrium, let me get the periodic table. These ones, and then these two are considered the rare earth elements. Now, the reason why they're called the rare earth elements has to do with the fact that they have very low natural abundances. It turns out that they're not as rare as they thought they were. It turns out that was just what was discoverable. It turns out that they're in far more abundance than what has been listed in this book, but they're still called the rare earth elements. Anyway, I'm just going through all this just to show you why I'm giving you this information, to keep it consistent with the book. But the one with the lowest atomic mass would be scandium. And again, the atomic mass is that number that is located right there in the periodic table. Now, the reason why I'm spending a little time discussing that they're not necessarily that rare is one of the things is that these rare earth elements are very valuable and have been used in a lot of electronics, and their discovery is obviously very, very valuable. Most of these rare earth elements are found in Afghanistan. So a lot of the deposits have been discovered there. So, if you're someone who follows if you're a political science person and you're just looking for where natural elements are and where conflict might be, anyway, that's the history of our planet, unfortunately. Okay, so the one with the lowest atomic mass will be scandium. Okay, the metal in group 7b/7 and period 4. All right, so see this periodic table here? This has labels across the top. Some are Roman numerals, others are just regular numbers that we use today. That's another thing that you're going to want to become accustomed to with a periodic table, is you're going to want to start numbering these columns. And the reason is it's going to ask you questions like what you just saw. The metal in group 7b/7. So ours would be just /7. The old way of labeling the periodic table had the Roman numerals. So I will always give you at least this version. I might give you both the Roman numeral and the regular number. But if it says the metal in group 7 and period 4, here's group 7, here's period 4, the metal would be manganese, Mn. Okay. So that's the basic idea there. Okay, so the next one, let's just see if you can get these quickly. These aren't supposed to be super hard, just get you familiar with where things are. The alkaline earth metal in the 6th period. You'd look here and realize that the second column is the alkaline earth metals. 6th period means 6th row. So alkaline earth in the 6th row would be barium. The noble gas in the 3rd period. Third period means third row. I go to the end. The last column is the noble gas column. You'll learn that if you haven't already by studying the names. Noble gases are the last column, so that'd be argon. The actinide with the highest atomic mass. It says right here, the actinide series. And we're going to go here. The one with the highest mass is nobelium, and it's right there. But I do want to point out that, notice this one has a different element here. So this is your introduction to the fact that not all periodic tables are the same. And you are going to see things like that. So on a situation where you're given a question like that, put the answer that is on the periodic table that's given on the exam. So I'm going to staple this exam or this periodic table to every single exam. So if I ask this question, just look at the periodic table I give you and say, okay, the actinide with the highest mass would be nobelium or NO. I'm not expecting anyone else to have the periodic table memorized, or you're not going to be having your own periodic table on the exam. So use the one I provide for you. Yeah, question? Yeah. Which one? Right. Okay, that's an excellent question. That's an excellent question. So her question, to paraphrase, and correct me if I'm wrong, is how come this isn't period 3? Because in the last chapter, we learned that the electron configuration, this would be the 3D block. So remember, that is the electron's configuration number that you assign. When we're talking about this, when we say period, we're talking about the entire row, not the electron configuration number. We're just if we say fourth period, we mean the fourth row, and in the fourth row would be 4s, 3d, and 4p. So when we say row, we're talking about the whole row, which would include 3d and 4s and 4p. So that was an excellent question to get that clarified. Okay, the semi-metal in group 3A or 13. So 13, we labeled right up there. The semi-metal, the only one there would be boron. All right. So hopefully that is pretty straightforward. So here is a blank periodic table. Now, one of the things that we're going to talk about and bring up electron configuration is what happens when you gain and lose electrons. So valence electrons, these are s and p electrons in the outermost orbitals, plural, possibly plural. Orbital, maybe orbitals, plural. So a question might be, how many valence electrons would lithium have? And you'd say, okay, that means the outermost electrons that are s and p electrons. So the outermost electrons would be the one in the last energy level. So lithium's in the second energy level, so it's second energy level electrons. It has a single outermost electron. And so lithium would have one valence electron, so one valence electron. But it turns out that if you look at this whole column, how many valence electrons does sodium have? Well, its outermost electron is that single electron in the 3s orbital. Same with potassium, except it's in the 4s. So it turns out that every single element in this first column has one valence electron. And if we look at the second column here, like beryllium, magnesium, and calcium, in their outermost orbital, in this case with beryllium, the second energy level, it has two electrons. It has lithiums, but then it has another one, the second s electron. Magnesium, calcium, and so on, they also have two valence electrons. So we put 2 right there. And basically what you're going to see is that if we come over here to aluminum, silicon. Aluminum would have 3 valence electrons, and boron would have, here's aluminum, here's boron, because if we look at aluminum, for instance, it would have this valence electron, this valence electron, and this valence electron. And its outermost energy level, it has 3. So we put 3, and then we go across until we get to the noble gases, and they have their last electron would be 2s2, 2p6 for neon, 3s2, 3p6 for argon. So these all have 8 valence electrons. So I want to make it clear that I have column number, which I've written here, but now I've written the number of valence electrons. Now, what's important about valence electrons is they're trying to get 8 valence electrons. That's the number that elements are trying to obtain because that is stable. So we're going to say 8 valence electrons equals stability. So every single element wants to have 8 and be just like a noble gas. Now the noble gases used to be called inert gases because they didn't react very well because they had all the electrons they needed. They didn't want to react with other elements to get more. So the idea is that these particles, let's say sodium for instance, it does not like having an extra electron. It wants to have a total of 8 electrons in its valence shell. It wants 8 valence electrons. In other words, every single element is trying to get a configuration of electrons like noble gases. So that's the driving force. They're trying to achieve what's called noble gas electron configuration. That's what the name of the game is. All right. So the way it happens is they will either lose or gain electrons to get that noble gas electron configuration, and in the process develop a charge and form what's called an ion. So an ionic charge is when you lose or gain electrons. Now remember, electrons are negatively charged. So if you gain an electron, you gain more negative charge, you become negative. If you lose an electron, you still have those positive protons that now no longer have their negative charge to balance it out, and you gain and you become positive when you lose electrons. And ions are the term for particles that have a charge. And by charge, we mean positive or negative. And positive or negative because it either has too few electrons or too many electrons. Okay. So the idea is that every single element in this column is going to want to lose 1 electron to be just like the noble gases over here. So sodium has 11 electrons. It would rather have 10 electrons, so it loses 1. Lithium has 3 electrons. It would rather be like helium with 2, so it loses 1. Cesium, 55 electrons. It would rather have 54, so it loses 1. So in other words, this whole column, every element is going to lose an electron to form an ion to get that stable electron configuration. And in the process, these will form +1 ions. The next column will lose 2 valence electrons because beryllium wants to be like helium with 2. Calcium, for instance, has 18 electrons. It has 20 electrons. It would rather have 18 like argon, so it will lose 2. So this whole column loses 2. And that's why every element in this column will predictably develop a +2 charge. So we go over here to column 13. This whole column develops a +3 charge. Now the reason why we're skipping the transition metals is because we don't consider the d electrons to be valence electrons. So that's why we skip them. Now, if we start here with the noble gases, they always stay neutral. No charge. But what do you think happens with fluorine? It has 9 electrons, and it wants to have a noble gas configuration. So what do you think it does? Does it lose an electron? No, it would gain an electron. Yeah, so over here, these lost electrons to have a similar configuration to the noble gases. These ones gain. So fluorine, for instance, will gain 1 electron to have 10, like neon. Chlorine will gain an electron to be like argon, and so on. So since this whole column will predictably gain a single electron just to have a noble gas configuration, they will develop a -1 charge. Because again, electrons are negatively charged. If you pick one up, now you're negatively charged too. Oxygen through and its family want to gain 2 electrons. So they pick up 2 extra valence electrons and become -2. The nitrogen family will become -3. Now we get to the carbon family. Now carbon and silicon and that family is a little weird. They can become up to +4 and down to -4 and everywhere in between, but we're not going to worry about these as ions, at least in this class. So we might see them just so you see them as examples, but I would never put something like that on an exam. Okay, so the idea is I want you to know what valence electrons are, the fact that they can be gained and lost, which brings on a charge. If you gain electrons, you gain a negative charge. If you lose electrons, you gain a positive charge. And those charged particles are called ions. The whole reason they're trying to form is these particles want to have a noble gas configuration. Okay, so that's pretty much everything in a nutshell, but of course, this is a chemistry class, so we have to make it a little more numerical than that. So let's talk about the electron configurations. We just had an exam on it, and so if we asked you what the electron configuration for sodium is, hopefully you would have just said, oh, that's easy. Sodium would be 1s2, 2s2, 2p6, 3s1. Right there, 3s1 would be the last configuration. All right, but we said that sodium can gain or lose electrons to become the sodium ion. So I'm talking up here, and it makes sense as you follow along, but what you're going to need to think about when I'm not here while you're at home studying, or in the hallway studying, or wherever you study, that sodium is going to form an ion, which means it's going to lose or gain electrons to become a noble gas configuration. What do you think sodium's going to do? Do you think it's going to lose an electron, or do you think it's going to gain an electron? It's going to lose, because it either has to gain 7 electrons to get 18 and be like argon, or it can lose a single electron to go from 11 to 10 electrons to be like neon. And it's going to choose to lose just 1, as this whole column will. So that's the first thing, is you know, and you don't have to write this if you understand, but I'm just going to acknowledge it's going to lose an electron. Now remember, if you lose a negative charge, that's the same as becoming a positive charge. So when we show sodium as an ion, we have to indicate its charge like that. And I'm putting the brackets around it just to kind of, make it stand out a little bit. So my question is to you, which one of these electrons do you think it lost? This one? This one? Yeah, so think about this, right? If you own chickens or animals, farm animals, and there's a wolf going to come and eat them, just like a wolf's going to come by and steal this electron, they're probably going to pick off the one that's the closest and easiest to get. And that's the same thing that happens with electrons too. Is something's going to come along and steal this electron really easily, and it's the one that's the furthest out. So it loses the furthest valence electron, the outermost valence electron. Outermost is lost. Okay, so the electron configuration would be 1s2, 2s2, 3p6. But in the business, we would say, you know what? That's the same as neon. So we would say that that equals just simply neon. So in other words, the electron configuration for the sodium ion equals the exact same thing as neon. And that's what we'd expect. So the term I want you to now learn is isoelectronic. This means same number and configuration, configuration of electrons. If something is iso, it means same. Electronic means electrons, so same electrons, same electron configuration. So sodium ion is isoelectronic with neon. Sodium atom is not. So this is sodium atom, sodium ion. Okay, so now we look at aluminum. And so first we need to write the electron configuration for aluminum, like you would have had if this had been asked on the exam today. So aluminum is right here in row 3, and it has a single p orbital electron. So it'd be 1s2, 2s2, 2p6, 3s2, 3p1. Okay. So aluminum is a metal, and it has an option here. It can gain 5 electrons and become like argon, or it can lose 3 electrons and become like neon. Well, I already indicated that this column forms a positive charge, so that means it loses electrons. This column would rather lose 3 than gain 5. So it's going to lose 3 electrons and develop a +3 charge. So let's just put a note here. It's going to lose 3 electrons to become like neon. Or sorry, to become like neon. So which electrons is it going to lose? Well, it needs to lose 3 of them, right? So yeah, it's going to lose this one, and it's going to lose these ones. So again, it loses the outermost electrons. It loses the valence electrons, to be specific. And so then it becomes just like neon, that we have up here. Same thing. So that's nice. We can shorthand that. Okay, so hopefully you're getting the idea. But now we have oxygen, and this is an example of something that's going to develop a negative charge instead of a positive charge. So here's the oxygen atom, and it would be 1s2, 2s2, 2p4. 1, 2, 3, 4. Oxygen has 8 electrons. It would either like to lose 6 and become like helium, or gain 2 and become like neon, which is what it's going to do. This whole column predictably gains 2 electrons. So it's going to gain 2 electrons, and then it's going to become, by the way, I wanted to write that this is aluminum with a 3+ charge. This is going to become oxygen with a 2- charge. Remember, you gain electrons, you gain negative charge. And an ion means a charged particle, so this is a negative ion. All right, its name happens to be the oxide ion. Okay, so the question is if you gain electrons, you have to put these electrons into the orbitals. Before, we were removing them, but now these 2 electrons have to be put in to those available p orbitals. So the oxygen ion would be the same as neon. In other words, it would be 1s2, 2s2, 2p6, where this 4 got these extra 2 electrons and turned into a 6. All right, so neon versus the neon ion. This is a trick question. The reason is neon already has 10 electrons, and therefore will not take on any more electrons. It's already stable. So neon will not lose or gain electrons. In fact, no noble gases will, because they already have the perfect number. All right. So one thing I want to mention now that we've talked about ions, positively charged ions are called cations. And it's easy to remember because a positive charge, you'll see that T for cation, positive charge. It's not pronounced cations, by the way, although when you do voice or text to voice, it will say cation usually. Okay, negative ions are called anions. And I don't have an interesting way like I do for the positive to remember that, but I can tell you it's not pronounced anion. It's anions. Okay, so that's a little more vocabulary to know. All right, so now we are just going to see how good you guys can follow trends. Now, I'm going to use this sheet right here just to show you you don't need to have the actual periodic table in front of you to solve this. In fact, I think in the back I printed an extra sheet. I didn't. Oh, right. So here's the deal. When you look at a periodic table, I want you to think of this arrow. And I'm going to point, I'm trying to go from the bottom left corner up to the top right corner. So I'm starting down here in the bottom corner, and I'm working up to the upper right. Down here to the upper right. So if you can be familiar with this arrow, that will help you follow certain trends. And one of the trends I want you to know is atomic radius size. So this is asking you to compare sodium and potassium and telling me which one has a bigger atomic radius. And an atomic radius, by the way, what it's talking about is if here's the nucleus, what's the distance from the nucleus to the outermost valence electron? So this is the radius it's talking about. And it just wants to know what that distance is. Well, the thing is, you can use the periodic table to follow this trend. And if you look in the bottom corner and you go from the bottom left to the top right, down here will be large. Down up here in the corner will be small. And the trend is that if you go up or to the right, you get smaller. So down here in this corner is the biggest, the smallest, and as you incrementally go toward the upper right, you get smaller. So we're just having you guys follow trends. So when you look at this and it says which one is smaller, sodium or potassium, you look at the periodic table and you say, okay, here's potassium, here's sodium. If you're up or to the right, you're smaller. So which one's smaller? The one that's more up or to the right, right? So sodium's smaller. It really is this easy. I'm not trying to trick anybody. I really want everyone to do really well on this. Like the concept is cool. I mean, you're talking about the size of an atom's radius, but in terms of you guys getting the right answer on an exam, well, that's a little easier. So I want to make sure everyone gets that right, but I also want you guys to know what you're talking about. But if we're comparing phosphorus and nitrogen, and we remember up and to the right is smaller, here's phosphorus and here's nitrogen. So which one's more up and to the right? Nitrogen. So if it's more up or more to the right or both, it'll be smaller. So nitrogen would be smaller. Calcium or nickel. All right. Here's calcium. Here's nickel. Which one's smaller? Nickel, because it's more to the right. Now, let me point that out. That is correct. Nickel is the right answer, and I'm even going to circle it, but I do want to acknowledge that that seems counterintuitive. It is smaller, even though it's more massive. It's heavier, has a bigger mass than calcium, but the trend exists. As you go left to right, you actually get smaller in the same row. So let's take a look at the next set. Silicon or sulfur. Here's silicon, here's sulfur. Which one's smaller? Sulfur. All right. Let's let the hopefully easiness continue. This is tin, believe it or not, and that's lead. Now, if you can believe me there, there's tin, there's lead. Which one's smaller? The one that's either up and or to the right. Yeah, so tin would be smaller. Awesome. Silver or strontium? Here's silver, here's strontium. Silver's smaller, exactly. Oops, this is metallic character. I didn't read this. Okay, back up. I was right. Tin is smaller than lead and silver is smaller than strontium, but then I forgot to read the question. So that's the other thing about getting test questions right. Read them. This one says, which one has the most metallic character? So we go here. If you like the idea that things are the biggest or the mostest or the greatest down here, we'll say this would be the most metallic. And as you go up and to the right, you're smaller and you're least metallic. So down here, bottom left-hand corner, most metallic, upper right-hand corner, least metallic. All right. So this one wants most metallic character, the most. So let's take a look here. Tin and lead. Remember, if you're down or to the left, you're more. If you're up and to the right, you're less. So which one has more metallic character? Lead, because it's more is down and to the left, so it is lower. So let me fix this. Lead has more metallic character. Silver or strontium? Here's silver, here's strontium. Now, silver might be the go-to metal that you think of when you think about metallic character because it really looks like you'd expect a metal to. Strontium, but in terms of placement, which one's more metallic? Strontium, because it's more to the left and or more down, so it would be more metallic. Awesome. Aluminum or boron? Which one is more metallic? So remember, with metallic character, in this corner you're the most, in this corner you're the least. So if you're lower or to the left, you're more. So aluminum would be more than boron because it's lower and or lefter. Okay, bromine or arsenic. So here's arsenic and here's bromine. Neither one of them are metals, and we're saying which one would have character that's closer to a metal. So it's still a fair question. Yeah, arsenic is more to the left, therefore it is more metallic. All right, any questions about that? Yeah.
Are you gonna like have a trick question, like if it was like carbon or phosphorus? Because carbon is lower, it's also to the right.
Okay, so I was gonna say that, and I'm glad you asked because it's always better when a student asks the question. The question is like, what if I gave you carbon and sulfur? And you're like, well, wait a minute, what's more important, down or to the right? Down is more important, always. Okay, great question. But the truth is usually to avoid the ambiguity, I sidestep it and choose questions that are more direct. So I'm not trying to trick anybody. All right, now, the last few slides here. Now this may be a little more complicated sounding than it really is. If you have some math background, this will fit in right into your math work possibly. But the idea is, as I mentioned before, that elements that are in the same column have similar properties. So if you're in the same family, you have similar chemical properties. Now, there was a time, believe it or not, that the periodic table wasn't known. It wasn't like someone dug up, some dirt and unearthed the periodic table and said, yay, we know all this information now, right? They had to figure this out, and the periodic table started off rather blank with just a few elements, and they were trying to arrange them. Well, one of the things that they discovered was obviously, as these columns started to be built, things like nitrogen, phosphorus, arsenic were realized they had similar chemical properties. Copper, silver, gold, all have similar chemical properties. They might look slightly different, but they have very similar chemical properties. So here are some properties that are being observed, and the idea was at a certain point, researchers knew information about calcium and strontium, but they might not have known anything about barium. Maybe that element hadn't been discovered yet. So let's say, for instance, they knew the atomic radius of calcium and strontium, and they were going to use that to predict what the atomic radius was for barium. Because if you know the atomic radius, it might help you be able to find it. So what they realized is that as you go down a periodic table, if the atomic radius is a given size distance between calcium and strontium, we would expect that same incremental size difference between strontium and barium. So what I'm saying is, I'm just looking for my calculator really quickly. Here it is. If the difference between 0.215 and 0.197, if that distance is 0.018 nanometers, then we would expect this distance from here to here to be that same amount. We would assume that that would also be another plus 0.018. So again, all we're saying is that because these metals are in the same family, if the difference from here to here is something, we would expect that same difference from here to here. So the difference from here to here is 0.018, so we'd expect that same difference here. So we would predict that the radius would be 0.233 nanometers for barium. All right, so just to see that in action over here, I'll go to this one, I'll do the middle one last. Melting point. So in this case, we know barium's melting point, strontium's melting point, but we don't know calcium's. But if we know barium and strontium, the difference there, we would predict that it would probably be about the same difference here. So we look at the difference in melting point. And as we go from here to here, that is 769 minus 725. So this difference is 44 degrees C. So it's going up positive in this direction. So what do you expect the difference from here to here to be? The same. So if from here to here is 44 degrees, then we would expect this also to be 44 degrees C. So we see it's going up. So we take that 44, we add it to this, 769, and we would predict that this would be 813 degrees C. So what we've done here, if you're a math person, is in this case, we notice that the atomic radius was increasing. So here's our atomic radius going up in that direction, and here's our element, calcium, strontium, barium. For this one, we notice calcium would be about here, strontium would be about here, and then we said if it goes up that much here, we would expect it to go up that same amount, and then we predicted that value. And that's called extrapolation. We did the same thing here with temperature. So we had calcium, strontium, and barium. We started with barium, and we noticed the temperature was here. Strontium, it was here. And then we said, okay, well, we'll use this difference here, and we'll extrapolate to this value. So we extrapolated. But now we're talking about density. So this is density. And I have, again, calcium, strontium, and barium. And what we're saying is that we know calcium's density is 1.54. We don't know strontium's. We know barium's, and it's more than twice as much. So calcium's would be here, barium's would be here, and somehow we're supposed to figure out what strontium's is. So how do we figure out something, here we had extrapolate, we'd extend that data out. Here we'd extend that data out the other way. But what do we do when the data we need is right here? Well, It's similar to extrapolation, except it's called interpolation. So if you extend data out further along a line, we call that extrapolating. If we get data that's between two other data points, we call that interpolation. And so this is the average of these two data points. So we're going to take the average. That's the easiest way to do it. If you're a math person and you have another way of doing that, just show your work and that's fine. So to get this value in the middle, I do 1.54 plus 3.65, and then I divide that whole sum by 2. And make sure you hit equals when you add these together, or your calculator may do crazy order of operation things. So 1.54 plus 3.65 equals, and then divide by 2. And I get 2.595, or 2.60 for the proper number of sig figs. So we would say this would be 2.60 grams per milliliter. All right. So that